My name is Alan Wong. I'm a software engineer at Google Cloud. And today we're going to be talking about scalable advanced ML systems with Ray, Google Kubernetes Engine, and ML accelerators. I'm joined today by some great speakers, some great guests, Wendy from Character and Richard from Anyscale. You'll be hearing more from them throughout this talk. Today's topic is going to be all about scale. So throughout the history of software, scale has always been a driver of innovation, and this is especially true for a field like machine learning. We're going to be exploring why scale is crucial for cutting-edge applications like large language models, like reinforcement learning, and we'll dive into some of the engineering challenges that are associated with it. What we'll find is that as computational requirements continue to grow as we continue to scale, it's vital to have powerful infrastructure that's able to support it. So we're going to be talking about why the combination of Ray, GKE, and ML accelerators can help you take your scalability to the next level. The history of ML innovation is marked by several profound moments in history that have come as a result of new breakthroughs in scale. Since AlexNet kickstarted the deep learning movement in 2011, we've seen a lot of great models come out. Muzero, GPT, Gemini, and each of these demonstrate superhuman capabilities across a wide variety of tasks. So it's been amazing that scale has always been a key factor in disrupting the way that we think about and interact with technology. So we can explain this by something we call scaling laws, or the relationship between data size, model size, and performance. What we find is that as our computational capabilities increase, so has our ability to process larger amounts of data with larger and more complex models. We've realized that this continuously unlocks more advanced predictive capabilities. But naturally, this raises a curious question. How far can these scaling laws take us? As we continue to explore the limits of these laws, it becomes crucial to have the ability to iterate and experiment quickly. Because behind the scenes, what happens a lot of the time is that these innovative breakthroughs are often the result of ML researchers who are efficiently utilizing a large amount of capacity and computation in well-engineered systems. So it's vital to have the ability to iterate quickly and increase our rate of innovation. While scaling laws and rapid innovation are generally relevant for a wide variety of tasks, reinforcement learning has an additional unique opportunity. So in reinforcement learning, what scale provides us is the ability to improve a model's decision-making by allowing it to interact with and explore its environment. This is key for developing RL models that can learn to adapt to complex and real-world situations. I think one of the most striking examples of the impact of scale in ML is the emergence of large language models, or LLMs. So many of these models have showcased the power of scaling laws in unlocking new capabilities and transforming the way that we interact with language-based AI systems. So I like to say that LLMs are like the poster child for when we talk about scale and innovation. And one of the main fascinating aspects of LLMs is this phenomenon where new capabilities seem to emerge spontaneously as the models and the data sets grow larger. So this has a lot of profound implications for how we can approach AI development. For instance, rather than manually engineering specific features or algorithms for individual tasks, we can focus on training larger and more powerful models that can learn and generalize from a vast amount of data. This is a foundational paradigm shift that opens up new possibilities for AI applications. It has the potential to accelerate progress in a wide variety of fields and domains. But the act of scaling LLMs is actually not simple. If we take this from an engineering perspective, we actually run into limitations very quickly. We have a lot of advanced hardware today that's capable of a lot, has a lot of computational power, has a lot of memory. But it struggles to actually meet the compute and memory requirements of these massive models. So we have to start utilizing complex engineering practices like model sharding. So if you take, for example, the fully sharded data parallel, or FSDP approach, which you can see visualized here, we're able to make clever usage of data sharding and the usage of collective communication protocols to train and fit larger models in one single device or across multiple devices. But techniques like this aren't actually trivial. It actually requires careful design and optimizations to ensure that we have efficiency and scalability. The point is, exploring the boundaries of scaling laws is actually as much an engineering challenge as it is an ML research challenge. If we want to push the limits of what's possible, it not only requires innovative algorithms, but it also requires advanced engineering solutions to make these tractable and efficient. But the impact of scale actually extends past large language models. In reinforcement learning, we'll find that scale plays a crucial role in enabling agents to learn from vast amounts of interaction data and tackle complex decision-making tasks. So with that, I'd actually like to hand it over to our next speaker, Wendy, who's going to introduce you to the world of distributed reinforcement learning at scale.
Yeah, I'm Wendy. I'm from Treasure AI. I'm a research engineer, and following Alan, I'm going to talk about another type of scaling. So when the term scaling LLMs usually refers to making the model larger and bigger. But there's actually another aspect of scaling that has unlocked a lot of remarkable ML capabilities, especially in reinforcement learning. That is scaling inference. The goal here is to actually, if there's a laser pointer over here? Oh yeah. The goal here is actually to train an agent to perform a certain task by deploying numerous actors to interact and explore the environment. Actors will send their experiences to a replay buffer, and the centralized learner will sample from the replay buffer to in turn update the inference model. Yeah. And this picture summarizes the typical setup. So first is you're going to have hundreds to thousands of actors interacting with the environment and sending their trajectories into a replay buffer. And then the learner will sample batches from the replay buffer to update the model, and lastly, broadcast the updated weights back to the acting side. For smaller models, we can easily deploy all the inference side on the CPU where the actors live on. But when these models get larger, or if we have a constraint in terms of CPU resources, a more scalable solution is actually deploy the inference into a dedicated inference server on an ML accelerator, which means the actor will send their observations to the inference server as requests, and then the inference server will process the data in batches. So many successful sort of RL applications have been derived through this type of distributed system. And I listed out the milestone works on the left-hand side. Particularly for AlphaGo, AlphaZero, and Muzero, they share a unique feature, meaning that when they're doing acting, they're actually also doing search and planning using a technique called MCTS. So today, we are actually going to demonstrate how to integrate Ray, GKE, and ML accelerators to work together, build such a distributed system using Muzero as an example. Similar to AlphaGo and AlphaZero, Muzero uses a technique called Monte Carlo tree search, or MCTS, to build a tree of many possible futures and outcomes based on the current state. And then from there, to make the optimal decision by looking into the future. So to simulate such, but unlike AlphaGo or AlphaZero, which uses real simulators doing this kind of simulation for possible futures, Muzero actually learned to predict a compact representation of future states alongside with value-reward action. Therefore, Muzero essentially is a model-based algorithm. And during search and planning through MCTS, it aggregates the values and policies through all these possible futures together through a technique called backpropagation. And using backpropagation, we can eventually derive an average and theoretically more accurate estimation of the value and policy of the current state. And these states will go back as a target for the learner to learn a better model for agents. And these agents will then be deployed to the inference front to get better estimates of value and policy for the next round acting. So this type of iterative improvement of policy and value is what enabled Muzero to refine its strategy over time. Muzero has demonstrated state-of-the-art performance in a variety of tasks. For example, from board games like Go and chess, to video games like Atari with dense reward, and to continuous control, like in robotics. But to enable Muzero, it requires a very robust and scalable, efficient system, since, as we can see, there are a lot of components going on in this distributed system. To be more specific, during the acting side, the actors need to plan ahead with MCTS. So here, it actually requires, also in the model-based manner, which requires two types of inferences. The first type is to process the current observation, which we refer to as representation network. And the second type is to predict the future state representations, which we refer to as the dynamic network. And these terms will come back later on. The second part is the learning part. Here, we will have the newly estimated value and policy through acting back to the learner, and the learner will use this as a target to update the current agent model. So what makes this scaling very difficult? First, there are going to be hundreds, if not thousands, of different workers doing different things. To orchestrate them together is really challenging. And second, during acting, we are actually using deep neural nets for inference to guide the action. Therefore, the inference load is humongous. And third, there's a lot of communication going on. For instance, the actor needs to send observations to the inference server sends it back, and the actor sends stuff to the replay buffer, and learner to extract from the replay buffer, and then send the model weights to the inference servers. So therefore, low latency is extremely important for this communication. And third is resource utilization. Because we have so many different components working on different parts, if one has to wait for the other because of an inefficient resource utilization, it will really slow down the entire system. And lastly is robustness. Since if one worker fails, it will bring down the entire system, then we will never be able to train an entire model. And to address these challenges, I'm going to hand it to Richard.
Hi, everyone. So I'm a product manager here at Anyscale, and I'll be talking a little bit about Ray and how it's here to solve a lot of the problems that were mentioned by Alan and Wendy earlier. So Ray, which is on the talk title, is an open source unified compute framework that makes it really easy to scale AI and Python workloads. It's sort of been around for almost 6-7 years and has grown a lot in popularity over the last couple of years. In particular, what does Ray do for you? It handles the orchestration, scheduling, fault tolerance, and all scaling and other aspects of the distributed systems so that application builders can focus on building applications, machine learning practitioners can focus on building their models, and, for example, the distributed reinforcement learning setups without needing to become a distributed systems expert. I'll show you a little bit about how Ray allows that sort of functionality to take place. So at a very high level, here are some of the characteristics about Ray. It's Python first, and it's an open source project. And in particular, the focus on Python allows it so that application developers and machine learning practitioners can easily sort of articulate programs using this sort of framework or library. Now, its API is simple and flexible, and I'll show you an example in the next slide. And there's a big focus on scalability for Ray, which essentially translates to being able to articulate single-threaded programs, but also be able to express distributed computation as if it was a single-threaded program. And finally, relevant to the TPU aspect, it does have support for the bleeding-edge hardwares, not only CPU, GPU, but TPU, inferentia, Gaudi, et cetera, as well. But we'll mainly focus on the Google stack here. So the Ray core APIs is really the foundational building blocks for which, if you are a practitioner, if you want to use Ray, these are the sort of three main concepts that you need to know. The first one is a task, and the task sort of corresponds to a Python function, right? So in Python, you have these functions. It's a properly scoped sort of language-specific definition. And all you need to do to turn it into array task or array remote function is by adding a decorator on top, which specifies ray.remote. In effect, this allows you to execute the task asynchronously, and it can execute anywhere in your Ray cluster. It's kind of like the serverless sort of programming paradigm. Now, the second concept is an actor, and it sort of maps to the Python equivalent of a class. So essentially what you can do is you can specify a class and you tag it with the same ray.remote decorator, and now you can spin up in effect a long-running Python process, an actor or a service, and you can interact with it in a long-running way as well. So now with these two primitives of tasks and actors, you can now easily program a distributed cluster and be able to create applications such as Muzero, which are a little bit more complex and require different components to be interacting with each other and communicating at high scale. The final thing to sort of make this all sort of work together is the objects that Ray provides. And so Ray does have an object store, an in-memory object store, and it's sort of focused on sort of data objects, being able to move tensors around very quickly. And the core concept here is that like if you have a Python object, being able to put that through Ray using ray.put or ray.get, that allows you to move these objects from one service or one node, one actor to another task or another actor very, very effectively through Ray's distributed communication protocols. So again, there's three main concepts for Ray: functions which map to tasks, classes which map to actors, and then objects which map to distributed objects. With these three primitives, you can actually build a lot of very interesting things. And in particular, with the Ray package, we've built a variety, Anyscale has built a variety of libraries for AI workloads. So instead of needing to sort of program these things from scratch, you have these higher level abstractions that allow you to articulate simple things or standard things such as data processing or batch inference, specifically for neural networks and stuff like that, being able to handle data at large scale, and having really good GPU and TPU support. Moving on, that we have Ray Train, which is built for distributed training. Again, sort of is targeting sort of the ability to scale your data parallel or model parallel training using PyTorch or JAX or whatever on various different clouds and different accelerator devices. RayTune is a hyperparameter tuning tool. It's integrated really well with other standard optimization libraries such as Nevergrad and so on and so forth, and also experiment tracking mechanisms such as weights and biases and MLflow. And finally, there's RayServe, which leverages a lot of the serving capabilities and makes it really easy for application developers or machine learning engineers to articulate their programs in a fault-tolerant, distributed, application-friendly way. So again, the high-level part about this slide is that Ray does have a set of high-level libraries end-to-end across the application lifecycle for machine learning that makes scaling just really, really simple and enables data scientists and machine learning engineers to ship their applications to production. Now, so tying it back to what Wendy and Alan had been talking about, why is Ray relevant for distributed RL and distributed machine learning in general? One big part is the support for heterogeneous resources. So you can imagine there are places where you want to do inference and you want to use a particular inference chip. Maybe there's parts where you want to do training within the same loop and you'll want to use something more standard like a GPU. And then you also have CPU intensive tasks for like, in-memory computation and things like that. So being able to articulate all of these things in a very asynchronous and distributed way makes it really easy for these sort of complex programs to arise. Low latency task scheduling is obviously important. So as mentioned in the RL situation, you have to sort of be able to send information from the replay buffer to the actors to the inference sort of servers and stuff like that. And that sort of low latency task scheduling needs to be there. And if it wasn't, then your application would be too slow to function, too slow to train. And then finally, flexible composition to orchestrate different models and components. It's sort of the whole story around Ray's sort of tasks and actors and why they're such low-level primitives. It makes it really easy for people to build things and enable applications such as distributed reinforcement learning to arise. So I'm going to talk a little about Ray and TPUs since this is very specific to some of the stuff that's being announced at Google Next today, and also relevant to some of the work that we've been doing with Allen and GKE and so on and so forth. So with, again, sort of having the Ray programming paradigm, if you used TPUs before, like it's sometimes you have to work through the CLI and it may be really hard and clunky to get right. But with Ray's sort of single-threaded programming paradigm, single controller model, you can now sort of scale your workloads across TPU clusters extremely easily within the Python world. So in this example, what we have on the screen here is we're just specifying that this function needs to run on a pod slice that has 4 TPUs, and Ray will do some of the scheduling to reserve 4 TPUs on the cloud and within the cluster. And you can obviously, like within this code logic, you can see that within the Python function is detecting 4 TPUs. Now, you can also sort of scale out the number of these functions that you call. For example, like you see device.remote for 128 different functions. And this will create 128 copies of the same function, run them in sequence or in parallel with each other, and you can see 512 sort of TPUs being reserved at the same time. And so why is this relevant? It's because a lot of training sort of happens due to the programming paradigm of the TPUs being single program, multiple data, SPMD sort of execution, which basically means that you take the same program and you execute it across different TPUs all at the same time. And they just need to run sort of in lockstep. Now, what makes Ray really relevant is that because of the simple ray.remote and ray.get programming paradigm, the ability to execute across the entire cluster of like thousands of TPUs becomes extremely simple. It just requires 5 additional lines of code added to your sort of existing distributed training or JAX or TPU logic. Again, so the way this happens is that like the orchestration happens by Ray, the TPU stack happens a lot of like the interconnect and intercommunication, and then all the stuff sort of gets abstracted from the machine learning developer so they can focus on modeling. So sort of like visually depicting what I'm describing here, what you have here is like a Ray head node, which is where the program runs, and it's connected to the entire TPU cluster. The way you connect it is through a simple Ray command that connects across the ports. And by having this sort of setup, the developer can go onto the head node and run code across the entire cluster and still sort of have the flexibility and the like the debuggability and the programming sort of simplicity of them sort of being on a single head node. So a lot of other things here, in addition to this building block, is that you can actually do really smart fault tolerance on top of this sort of large-scale system. And so, for example, you might have pods that go down here and there. Being able to have a single place where the control plane is sort of managed allows like the fault tolerance to sort of easily be addressed, and you're programmed to sort of continue executing without needing a lot of manual intervention. So I guess within Google, there's been sort of a large number of jobs on cloud TPU pods that have been run in order to automate like hyperparameter sweeps and perform performance optimization searches and sort of take advantage of this programming paradigm. So like the other added thing here is that Ray can also allow you to connect different pods together to sort of enable even more scaling capabilities, all without sort of adding more added complexity to your code. And so this is super important for serving use cases or like parameter sweeps where there's no need for a deep interconnect within your TPUs. Similarly, it's like if you have problems scheduling large jobs because your TPU allocation needs to be very large and you don't actually need the interconnect, Ray sort of solves that problem for you because you can now sort of conjoin a bunch of small TPU pod slices together. So now I'm going to hand it back to Alan, who's going to talk a little bit about more TPU stuff.
Thanks, Richard. So I'm actually going to talk about how this stack can be used for Ray and Muzero, which is the task that Wendy was talking us through before. So in collaboration with Character, we've introduced Muco, which is our fully open sourced cloud-first re-implementation of Muzero, which is actually now available on GitHub under Character AI's GitHub repository. We've been very interested in exploring how Muzero's environment-agnostic capabilities are able to apply in other contexts. So for instance, LLM reasoning. As we started working on this project, it became very apparent to us quickly that reinforcement learning was challenging from an ML perspective, but it was also very challenging from an engineering perspective. Wendy had already previously highlighted the complexities of the Muzero setup, which consisted of a variety of other components that interacted with each other in fairly intricate ways. So in order to model these components and their interactions, we encountered several technical challenges. First is that a single workload typically consists of a large amount of ML compute on the cloud, which generally requires heterogeneous ML accelerators. So we needed a way to provision, orchestrate, and scale a large amount of compute in a robust way. Second, machine learning workloads, including RL, typically run for a long time. And so compute failure at the scale is typically inevitable. So it's critical that our running workload has some type of fault tolerance or some resiliency mechanisms in place. So for Muzero specifically, we needed a way to orchestrate and maintain the state of a large number of processes that were interacting with each other in very specific ways. And then we finally needed a way to implement the modeling components in a way that was hardware agnostic and also gave us good performance. So to tackle these challenges, we used a stack that was built entirely in open source technologies that perfectly fit our needs here. So our stack actually leverages TPUs as our ML accelerator of choice, and we provisioned and orchestrated these with GKE. Sitting on top of GKE, we used Ray as our unified distributed computing framework, and then we used the Jackson Flax stack for our modeling components. This actually gave us a lot of advantages. So starting from the JAX layer, thanks to its tight integration with the XLA compiler, it actually allowed us to define all of our components in one single hardware agnostic way, which enables seamless and efficient execution of our models with the ability to target different backends. So we actually are able to define the JAX components once and then have that run on CPU, GPU, and TPU. Ray is essential in modeling the interactions between our various components and allows us to model some fault tolerance in pure Python. So Ray's single controller architecture and simple API with remote calls makes it actually easy for us to start and maintain the processes and allow them to communicate with each other and really simplified our development workflow. GKE's self-healing capabilities gives us a robust infrastructure that allows us to quickly recover from any failure. And so when we combine this with Ray through KubeRay, we're actually able to efficiently handle many machine interruptions and maintain the resiliency of our long-running workloads. And then finally, by leveraging an ML accelerator like TPUs, we're actually able to significantly speed up our training process in a cost-effective way. So we found the stack to be flexible, robust, and powerful. So let's actually talk a little bit more about individual details. OK. So at the center of our interacting components is Ray. As Richard mentioned earlier, Ray is hardware agnostic, which means it supports heterogeneous accelerator types. So what this allowed us to do is actually allow us to schedule these components regardless if the underlying hardware was a CPU or a TPU. For a quick recap, we have a lot of these actors in our stack, and these actually run on CPUs, and they rely on networks that are hosted on TPU servers to receive what we call representations and actors. There's a replay buffer here that relies on the actors to generate episodes or experiences. And there's a learner involved here that's responsible for training on these gathered experiences and transmitting checkpoints to the relevant components. So this Ray runner here is actually responsible for a lot. It's responsible for maintaining the interaction of these components and allows us to do this in pure Python. Let's also talk about how it helped us with our resiliency. Our resiliency is actually fairly straightforward. Our protocol was pretty much, if a critical component like the learner or the reverb server failed, then we simply reset the entire cluster to maintain our consistency and then continue running the workload. If a non-critical component fails, such as an inference server or an actor, we're able to actually just restart them in a way that minimizes the impact on the rest of the system, which allows us to quickly recover from failures while maintaining the stability of the other components. This granular approach to fault tolerance allows us to minimize our downtime, which ensures that our system can adapt and continue running smoothly, even in the case of what would otherwise be catastrophic hardware failures. What we found remarkable was that this was all implemented in Python thanks to Ray, which allowed us to actually engineer a lot and really test our systems confidently before we actually pushed out a large-scale training workload. And so this really allowed us to develop and focus on writing our resiliency strategy rather than getting bogged down in complex implementation details that other platforms might have required us to do. Our final challenge we encountered was actually optimizing the efficiency between the communication between the actors and the TPU servers. So it's important for us to minimize this communication latency in order to maximize our hardware utilization of the TPU servers. So to do this, we actually used a pretty common trick in both reinforcement learning and in ML serving systems, which is called batching, which essentially means like we'll collect many requests into a single batch and then perform one inference on a collected batch. So what we required here was actually a way to have low latency communications while still being able to leverage the power of Ray and JAX, which were both written in Python. So for this, we actually implemented our own custom gRPC-based request batcher in C++. And we designed it in a way that allowed us to still maintain the interoperability with the Python layer. So what ended up happening was that this allowed us to get really low latency thanks to C++, but still maintain interactions in Python, which was vital so that we didn't have to rewrite our stack and still maintain the power of Ray and JAX. I was really impressed by the ability to implement something like this in the C++ layer, but still fit in the Ray ecosystem. It really showcases the flexibility and extensibility of the Ray ecosystem. So overall, I would find that Ray's ability to seamlessly integrate with custom components, even one that we wrote in C++, allowed us to work through our specific requirements rather than sacrificing the benefits we saw with the rest of the stack. So in conclusion, throughout this presentation, we've explored the importance of scaling ML workloads and the complexities that are involved in building advanced systems. We've seen how the combination of Ray, GKE, and TPUs allow us to form a powerful stack that abstracts away many of the complexities that are associated with scaling infrastructure. By leveraging the strength of each of these technologies, we've been able to build systems that are resilient, efficient, and scalable. And because this abstracted away a lot of complicated details, it allowed us to do what we do best, which is actually focus on ML model development. We think that this will help ML practitioners achieve more at scale, and we're excited to see what you're able to build with this stack.